Right, so for the second talk today, we're very pleased to have Dranowski, who's going to tell us about generalized orbital varieties and MV cycles. So take it away, Anne.
Thank you, Jeremy, and thank you, Peter, for the invitation. I think this is my first official conference talk, so exciting. So yeah, the title of my talk is Generalized Orbital Varieties and MV Cycles, and I'll probably go a little bit off script from my abstract, but we'll see what we can cover. Oops. Sorry, there we go. Okay, so I want to start with a fact about matrices in the middle of nowhere, sort of. So if I have a matrix that looks like this, a block matrix with an upper left submatrix n-2 by n-2 matrix C, and these two columns V and W in Cn minus 2, and 1 right here, so the lower 2 by 2 diagonal block is sort of a Jordan block. And I assume that my matrix A has Jordan type lambda and my matrix C has Jordan type lambda prime, which viewed as nested Young diagrams differ in exactly 2 boxes. Then the assumption on what A looks like actually forces those 2 boxes to not occupy the same column, and the intermediate submatrix B to have a Jordan type which differs from that of A in the rightmost of those 2 boxes. So it's, I think, kind of a cute matrix fact, but it's very useful in proving something quite technical. So roughly this is saying that there is a natural order on the Jordan types of submatrices like A that we can maybe try to label collections of such submatrices by semi-standard Young tableau using this fact. So let's see where we can find these types of matrices. They show up, it turns out, when we consider the action of T just by multiplication on the affine Grassmannian, which I'll present here as usual as a coset space, K points of G mod O points of G, K denoting Laurent series and O denoting power series in this indeterminate T, but only in type A, where we have at our disposal the lattice model for the affine Grassmannian. So a lattice is a free submodule of the vector space Km, such that if I tensor with K over O, then I recover Km. And when G is equal to GLM, because I have an action of Km on Km, I can use the orbit stabilizer theorem pretty easily to identify this coset space with the set of lattices, such free O submodules. In addition to a weight of GLM, which in this case is just an M tuple of integers, I can associate various special orbits in the affine Grassmannian. And the one that will yield such matrices, as we'll see in a minute, I will denote by GER lower mu, and I won't define it, but just to know that it is an orbit in GER through a point associated to a weight of GLM. If the weight mu is a non-decreasing tuple of positive numbers, so can be viewed as a partition of size n, then any element of this orbit is a sublattice of the standard lattice, L0. And so we can look at the action of T on the quotient of L0 by L. And in some preferred basis, this matrix is going to be a nice looking block matrix with blocks of sizes given by our partition mu. The collection of all such matrices will denote T sub mu. And the subset of upper triangular mu by mu block matrices like this is a particular subset of those CVW1 matrices from the earlier slide, assuming that that last block is at least size 2. So let's get a visual on this set. If mu is the weight 322, for example, again, without really knowing what Gur sub mu is, let me ask you to take it on faith that if I take a lattice in Gur sub mu, then the matrix of T on the quotient of the standard lattice by this element will take this general form. So, you know, there might be something different going on depending on what I choose L to be, where those asterisks are, but the block form is always the same. And here there is a prime that stands for a transpose, so this is true up to transpose. So we can see that taking up a triangular such matrices exactly gives us this block matrix where I have my C, a V column, and a W column. And I can maybe try to apply that fun matrix back to elements of this T mu. Let me just say as another example, when mu is the all ones weight, then T mu is simply M by M matrices. And the theorem doesn't apply, but neither is it really necessary. In this case, we can label matrices by tableau without any ambiguity. This connects to the theory of just ordinary orbital varieties and their labeling by standard Young tableau. Okay, so this process of taking the matrix of T on the quotient of the standard lattice by a lattice in this orbit Gur lower mu is actually an isomorphism on a subset of T mu, which depends on a choice of a second weight or partition, lambda greater or equal to mu in the dominance order. So roughly visually a lambda that's a little bit wider than mu, but having the same size. And Mirkovic and Vibornov, whose work this is all based on, have shown that this T mu is actually a transverse slice to the conjugacy class of Jordan type lambda, of n by n matrices of Jordan type lambda, denoted O lambda, and that the intersection of T mu with the closure of those matrices is isomorphic to a special slice in Gur. So again, also depending on that second weight lambda, and this is also an orbit, but this time it's sort of easier to say explicitly it's the geo orbit associated to that weight. So as a corollary to this Mirkovic and Vibornov isomorphism, we can show that if I look at upper triangular mu by mu block matrices, then that subset, that half-dimensional subset of mu by mu block matrices in the closure of Jordan type lambda matrices is isomorphic to a half-dimensional slice on the other side, which may be more familiar to those of you who have seen a talk that involved something about geometric satake. Here, S mu, again, yet another orbit associated to a weight of G, easy to describe, is the U minus K orbit through the point associated to that weight, where U minus is just the subgroup of GLM of unipotent lower triangular matrices. So one's on the diagonal, And yeah, I just want to highlight that on the left-hand side, we have n by n matrices, whereas on the right-hand side, we can also view representatives of elements of the Grassmannian belonging to this slice as matrices, not just as lattices, but they're going to have a different size. And that size is fixed. It depends on the group that we fixed, GLM. Whereas on the left, we do have a fixed M that's also dependent on the group. We can view those parameters lambda and mu as weights of that group. So they'll have M parts always, but they'll have different sizes. And on the left-hand side, or we can describe sort of this slices of the same Grassmannian on the right by different sizes of matrices on the left. Okay, so for the rest of the talk, my goal is to survey various results related to this restricted isomorphism, starting with giving a decomposition of the left-hand side by generalized orbital varieties, indexing these by semi-standard Young tableau using our fun matrix fact from the beginning, and matching this decomposition of by generalized orbital varieties with a decomposition of almost the right-hand side. So not quite, because what we had was a closure, intersect S mu minus, but matching it up with irreducible components of the closure of that intersection, which are by definition the MB cycles. And I won't get to talk much about that. So if you haven't seen it before, it is something for the breakout room I'll leave. But yeah, the right-hand side is well studied, and the MB cycles, the irreducible components of this intersection, are important in geometric representation theory. Okay, so we'll start by, we'll start with the left-hand side. So how are these generalized orbital varieties built up? They're built up using a Spaltenstein type recipe and this matrix fact from the very first slide to a tableau, to a semi-standard Young tableau, tau of shape lambda and weight mu. We can associate a mu by mu block upper triangular matrix by requiring that the upper left submatrices of A, made up of the first I by I mu blocks, have a Jordan type determined by that the shape of the tableau restricted to boxes of weight 1 up to I. So we'll see what this means in an example, but the shorthand for this recipe is A sub I is in the Jordan, has Jordan type lambda I for all I. Okay, so by example, what am I doing? So to a tableau here of weight 2, 2, 1, the weight is telling me just the multiplicities of those numbers which occur in the tableau. I'm gonna assign a sequence of tableau, exactly 3, exactly as many as there are numbers occurring in that tableau, formed by just restricting it to boxes of weight 1, 2, boxes of weight 1. So altogether 3, including the tableau itself. And therefore 3 Jordan types, right? 3 Jordan types starting with 3, 2, and then 3, 1, and 2. And I'm going to use the information of those shapes of those Jordan types to define a set of matrices, again having this 2, 2, 1 block form, where I require that the upper left 2 by 2 submatrix has Jordan type 2, and that the upper left 4 by 4 has Jordan type 3, 1, and that the entire matrix has Jordan type 3, 2. So requiring that puts some constraints on my a priori unconstrained entries of this T mu. I can slow this recipe down, and instead of just assigning 3 tableau to a tableau of a weight with 3 parts, all of 5 tableaux. So if it's a size 5 tableau, I'll assign 5 tableaux to it by breaking off 1 box at a time, so that I get 5 shapes or Jordan types, and then 5 conditions on a 5 by 5 matrix, where I now put those conditions on upper left submatrices, sort of one at a time. And again, here's just a shorthand for this recipe in general, but hopefully you can see from the picture what I'm trying to describe. And note that there is some ambiguity in how I assign 5 tableaux to a semi-standard Young tableau. I could also maybe have broken off the lower 2 here, but it turns out that that's just not the right thing to do. And it goes back to that matrix fact from the beginning. Because of the ones here, it won't make sense to try to enforce such a sequence of conditions. Okay, but the point is that we can use this CVW1 matrix fact from the start to show that slowing this recipe down doesn't alter the result. We actually get the same set of matrices, but a more tractable way of finding a more tractable description. So one which lends itself to more easily finding equations, an ideal for this set. We're going to denote this set by x tau circle. The circle is there to say that it's kind of an open set of conditions. We've thrown some stuff away to make sure that those Jordan types at the various stages of this process hold on the dot. So like in our earlier example, we didn't allow for some of those entries to be 0, but otherwise they were unconstrained. And we're going to, okay, before we take the closure and define generalized orbital varieties, I want to say that, again, slowing this recipe down is useful for proving things about this set. For example, by induction on this restriction map that takes an element A of x tau circle to its upper left n-1 by n-1 submatrix. So an element of x tau minus m where I've thrown away the rightmost box according to my recipe labeled by m. By induction on this restriction map, I can show that x tau has a unique irreducible component of top dimension, of maximal dimension. And therefore I can define an irreducible variety x tau by taking the closure of that top dimensional component. And this is what I call a generalized orbital variety. Because again, in the case that mu is the all ones weight, then this recovers the ordinary orbital varieties, which are well known and were studied by Joseph and Melnikov and various authors. So this gives me a piece of the goal, which is the restricted Mirkovic-Vybornov isomorphism, describing results related to it, namely the left-hand side, this half-dimensional 3-way intersection, has irreducible components given by these generalized orbital varieties. And the main theorem, the main result that we have is that the closure of the image of these generalized orbital varieties x tau under this Mirkovic-Vybornov isomorphism is an MB cycle. The closure of the image of a given generalized orbital variety is an MB cycle on the right-hand side, so just an irreducible component of the right-hand side, but can be matched up. So there is some combinatorial datum that you can associate to an MB cycle called the Lusztig datum that comes from the crystal structure on MB cycles. That is due to work of Kamnitzer and Anderson. and semi-standard tableau, they also have a crystal structure, so you can similarly associate a datum to them. So just by matching up combinatorial data, you can start with an MV cycle and locate a generalized orbital variety, which gets mapped to it. Okay, so this is very useful for finding equations of MV cycles, which you might be interested in if you, say, want to compare the basis that you get from MV cycles to another basis. So this is switching gears. An application of this result, kind of indirect, is a wholly different question. So Baumann, Kamnitzer, and Knutson were interested in comparing two geometric bases of representations of algebraic reductive groups, the MB basis and the dual semi-canonical basis. And we won't go into how they're defined, but just to say that they are both bases of they're both bases of representations of some group, but that can be viewed simultaneously as bases of the coordinate ring of the unipotent subgroup of some group, some fixed group. Say GLM is one that you can have in mind, matching up the group defining this affine Grassmannian where the MB cycles live. So the indexing set here, the varieties set here, are just the MB cycles. And well, the dual semi-canonical basis is indexed by a different construction entirely, but modules for a preprojective algebra that has to do with the group G that is the main factor in the MV construction. Okay, so we'd like to compare these two bases of CU. And both are crystal bases. So again, they have some nice combinatorics. This is kind of an old result, and well, two separate old results, but relatively by now. But the fact that they have compatible polytope models is relatively new and is due to Baumann, Kamnitzer, and Tingley. And what that means is, so I have my geometric basis that relies on some geometric construction, and I claim, well, it has some nice combinatorial structure. That combinatorial structure is an abstract structure, but can be modeled concretely on polytopes. But those geometric constructions each come equipped with their own sort of intrinsically defined maps to polytopes. So in the case of the MB cycles, we can take their moment polytopes, and this whole triangle will commute. And in the case of the modules, we can take their Harder-Narasimhan polytopes. So we have compatible polytope models such that polytopes of Z and M are equal whenever the basis vectors indexed by Z and M give the same crystal datum. But this polytope model is a very interesting model for a purely combinatorial structure because polytopes are not purely combinatorial. So Kamnitzer and Knutson asked the question, well, does it actually remember some extra information about these geometric constructions? Given this, can we conclude that the corresponding basis vectors are equal? Maybe that's too strong of a question, so let's ask a weaker version of this question. So they asked, what about some function of those basis vectors? Well, we have another triangle, which is, we replace the crystal structure by a perfect basis structure. This is a definition due to Bernstein and Kazdan. Oops. And shown by Baumann, Kamnitzer, and Knutson that that the structure is enjoyed by both of these bases. But again, it's a similar structure, it's a similar triangle, but sort of upgrading all of the structures. So to our Z and to our M, we can now assign honest basis vectors. And we can also assign either directly to these basis vectors of CU measures or to any element of CU measures, but in particular to those coming from our geometric constructions, or intrinsic to those geometric constructions, we can assign measures and compare whether those measures are equal. Okay, so the answer is that the polytope model does not remember extra information, and there is a counterexample. And this is sort of our contribution to this question is using the description of generalized orbital varieties and using the fact that these guys map into and can be used to find equations of MV cycles. We can check the counterexample that corresponds to a generalized orbital variety labeled by this tableau. We can find precisely the ideal of that orbital variety. It is quite complicated, and checking that D of B of Z is not equal to D of psi of M, the two basis vectors in this particular example, relies on actually checking that the Fourier transforms, that the leading coefficients of their Fourier transforms are not equal, where on the Z side, that Fourier transform is an equivariant multiplicity at a fixed point of the MB cycle, which is computed using the information of the ideal of the corresponding generalized orbital variety. Okay, and I think, oops, yeah, so counterexample, wrong notation, should be psi M and BZ. But I think that that is the last thing that I wanted to say, so thank you very much, and lots of details kind of very quickly there, so if you have questions, I'd be happy to answer them in the breakout.